Welcome to Plate Tectonics. Our objective is students will be able to identify the layers of the Earth and synthesize Alfred Wegener's theory of continental drift. During the formation of the Earth, heavier compounds and elements were pulled towards the center while less dense materials stayed near the Earth's surface. There are three layers of the Earth. The outermost layer is known as the crust. It is the thinnest layer at 5 to 100 kilometers thick. There are two types of Earth's crust, which are oceanic crust and also continental crust. Although we have never been to the mantle, we can study the material that comes up from the mantle to the Earth's surface. The mantle contains 67% of the Earth's mass. Central part of the Earth below the mantle is known as the Earth's core. It makes up 33% of the Earth's mass, and it's mostly made out of iron and also nickel. The solid outer layer of the Earth is made up of the crust and the upper mantle. We refer to this as the lithosphere. The lithosphere is anywhere from 15 to 300 kilometers thick. The soft plastic-like layer of the mantle on which pieces of the lithosphere appear to float upon is known as the Asthenosphere. The lower, stronger part of the mantle, where rock is very highly compressed, is known as the Mesosphere. The Mesosphere is approximately 2,550 kilometers thick. The Mesosphere extends from the bottom of the Asthenosphere to the core. It has a depth of about 350 kilometers. The pressure in the Mesosphere is so great that even though the rock is very, very hot, it's still a solid. The liquid layer of the core. It lies beneath the mantle and completely surrounds the inner core. This is known as the outer core. And the solid dense center of the planet is the inner core. It's mostly made out of pure iron and a little bit of nickel. Because it's surrounded by the liquid core, this creates the magnetic field that supplies us with all kinds of protection against the sun's solar winds. Tectonic plates are pieces of the lithosphere that move around on top of the Asthenosphere. They sort of look like they fit together like a puzzle, but we're going to take a look at their relationships to one another. As you can see at the red arrow, it's pointing at the border of the Australian plate and also the Pacific plate. The Pacific plate, of course, is hidden by the Pacific Ocean. If you look over at the blue arrow, you'll notice the Pacific plate has a border also with the North American plate. And the green arrow, you can actually see where the North American plate is touching the African plate. And when we eventually will look at a current map of the United States and also Europe and South America and Australia, if you look at everything, it sort of looks like it can fit together like puzzle pieces. And this did not go unnoticed by a scientist by the name of Alfred Wegener. He believed that all the land masses were once locked together and have moved apart through the Earth's history. He actually wrote about this theory and the theory of continental drift. This was originally as a hypothesis that all continents formed a single landmass that he actually named Pangaea. Besides the puzzle-like shapes of the continents, Wegener also found rocks and fossil evidence to support his theory. Let's take a look at his map. He found similar rock sequences on both sides of the Atlantic, along with plants. The plant's name was Glossopteris. It's actually shown, the trail of Glossopteris is shown in South America, Africa, Antarctica, and also Australia. And it is shown in this map depicted within the green. And this is an actual photograph of the fossil of Glossopteris. And we also have an artist's depiction of what the plant actually looked like. In addition to Glossopteris, he also found fossil evidence of what's known today as Lystrosaurus. This is a dinosaur that was found in Africa, India, and also Antarctica. It's depicted in the red in the map, and this is a fossil evidence of Lystrosaurus. Now the yellow that's depicted in the map of South America and also Africa at the very bottom is Mesosaurus. And what Alfred Wegener was convinced of was that this animal could not swim an entire ocean from one continent to another. That this particular animal had to have inhabited Pangaea. And finally, we have Cynognathus. This particular fossil was found on South America and also Africa. It is depicted on the map as the blue section. And as you can see, they have also an artist rendition of the skeleton of the fossils of this particular dinosaur. So Alfred Wegener's thought, if you can look at his train of thought by looking at the map, we've got the blue, the green, the red, the yellow, and we've got plants and animals that look as if they were inhabiting one large landmass known as Pangaea. And it's not really all that far-fetched. If you look at the different continents now, the different continents have different types of animals, for the most part, that are in particular to those areas. Think about Australia. You know, when you think about Australia, you think about the kangaroo. If you think about elephants, where do you find elephants? Well, you do have African elephants, and then you do have Asian elephants, but you can see differences. He was actually looking at a specific species of plant and also specific species of dinosaur that was found in several different continents. It must have come from a large landmass. Even with the evidence that Wegener had already, many scientists would not accept his theory of continental drift. He even had evidence of glacial trails that actually skipped from one continent to the next, and then when he put it all together like a puzzle piece, these glacial trails actually connected. But the scientist would not believe him because he could not come up with a mechanism that could explain how the continents were moving apart. The evidence that he needed for his theory did not come about until after his death. In the 1950s, scientists began to really study the ocean floor using sound navigation and ranging technology, sonar, to look at the topography of the ocean floor. And what they found was the mid-ocean ridge. What scientists now know is that seafloor spreading is involved, and this is the actual mechanism that Alfred Wegener was looking for. What was causing the continents to drift apart was the convection current that's found in the mantle is actually pushing up. The less dense material is rising up to the ocean floor, and as it comes in contact with the water, it hardens and it becomes part of the ridge system, and the ridge system actually pushes in either direction. It is a divergent boundary, and as that divergent boundary pushes to the right and to the left in this diagram, eventually it will come in contact with the continental crust, and of course that will push those plates further and further apart. So evidence of seafloor spreading is shown with magnetic reversals of the Earth's magnetic poles. This evidence was found by the geologists who studied the ocean floor. As you can see in this graphic, the black stripes represent rock that is facing north. The white stripes represent rock that is facing south pole. And what this shows is that our magnetic field has flipped several times throughout the Earth's history. In fact, it's 170 times in the last 100 million years, according to the evidence that's found on the sea floor. This, of course, was more information and more evidence for scientists to say, hey, look, there is a mechanism here that Alfred Wegener did not know about that can cause the continents to move. Once scientists had actually found the mechanics behind the movement of the plates, they started taking a closer look at the boundaries. Number one, the convergent boundaries. 2, the divergent boundaries. 3, the transform boundaries. Before you learn about what causes plates to move, you've got to learn about the different types of tectonic plate boundaries. First is the convergent boundary, and this is found when two continental plates collide, and as a result, they form mountains. The second type of boundary is a divergent boundary. We've already briefly talked about this. Divergent boundary, like the mid-ocean ridge, is where less dense material makes its way to the surface. It hardens, solidifies, and pushes the plates, as in the picture, to the left and to the right, eventually hitting continental plates and moving those continents. And the last type of boundary is the transform boundary. This, of course, is a strike-slip fault, and it's when two tectonic plates slide past one another horizontally. And of course, we know this to be what is underneath Los Angeles. Actually, it's in San Bernardino County in California, and it's known as the San Andreas Fault. So there you have it. Students will be able to identify the layers of the Earth and synthesize Alfred Wegener's theory of continental drift. I think we've gone over all the layers of the Earth, and I do believe we went over Alfred Wegener's theory of continental drift, and as a result, we have plate tectonics. I hope you enjoyed this, and I'll see you next time.